So my name is Sebastien Heymann, and I will present you Gephi, but more than that, I see that during this course, you see many techniques about information retrieval, graph modeling, and how to rank information. Well, techniques is very good, but here I want you to think something maybe differently. I mean, we'll think more about getting some data somewhere in the world and trying to figure out if we can see them as networks. And by seeing them as networks, we can get novel information, finding novel ways to see the world, extract meaningful information from them. And using this approach, we'll use a tool which is called Gephi. Well, I'm very young. I mean, I'm only 26. It's my second year of PhD in France. And we started this project with a friend when we were at the university. So it is an open source project that grew very fast, and people started to love it very, very much. And researchers, companies started to use it. And so we stick on the project, trying to reply to all the demand and see what's going on. So it's a great pleasure to be here. It's my first time in Russia also. And well, you can hear that I have a very strong French accent. So please don't hesitate also if you don't understand something that, okay, raise your hand, please can you say it again? And I will try to explain a bit more. So that's fine with it. So during this course, what you'll see is an introduction to networks and how we could see the world as networks. Maybe if you currently you have seen web graphs, and web graphs. You can have many other data that you can see as a network. Not everything can be modeled as networks, but for many, many different areas, it's just a matter of imagination. And maybe we can find something very interesting in it. So let's start by where is it? Yeah, all right. Maybe you know, of course, these kind of networks. Well, social networks of terrorists on the left, Facebook on the right. Many intelligence agencies like CIA and others use social network analysis for a long time to try to figure out who is the head of these distributed organizations. And because we are more and more involved in the digital technology, we use the web, we give some information about us, we let social traces, we use services, and all of this information can be used also to better understand how we interact with each other, and also, most important for companies, who you are, what are you interested in, which advertising can I target to you. And this is, of course, a very obvious network that you can directly address, but you can find many other areas that you can imagine as a network. So, well, so for instance, softwares. Well, I know you like computers. You can imagine source code as a network. For instance, you have methods calling other methods, and okay, you can start to have a graph. It's not really used by companies, but some experiments are able to analyze. You parse your code, you create this kind of map, and after that you start to analyze if your code is loosely coupled or very modular, or it is just a spaghetti code and you need some refactoring, or it can be very dangerous. Maybe also to find, okay, you have a bug, where does it from? maybe you identified it in one area of the code, but it is maybe because of different particular other elements. And so maybe networks can be very useful to better understand and better fix bugs. But there are many other areas where you maybe could find networks. And I will need your help for it. So imagine networks. Well, it's very simple. Well, I will use many different materials during this course. I don't have the monopoly of network analysis, and there are free courses available in many places, and they are very great. So I don't reinvent the wheel. I will use big different areas, and it will be also some good pointers for you if you want to go deeper in the field. You will have some very good references. So for instance, in the University of Michigan, there is a very good course on social network analysis. And just to be clear, what is a network? It is just a matter of vocabulary. For me, a network is a graph. It is, you can have nodes and edges, you can call them whatever you want, ties, relationships, bonds, links. It depends on your field you're from, but well, it doesn't matter. Just to be sure that we share a common vocabulary, I will always talk about networks, nodes, and edges, and sometimes relationships. Just also to be clear, so you can have, maybe you are already, tell me also if I say some obvious things here. So for me, a network can be directed or undirected. So if the direction of the relation matters or not. And you can have also weight on the edge. So it's just a number, but it will mean anything for you. I mean, also, nodes and edges could mean anything. We talk about networks, but we mostly think about real-world networks, infrastructure network, internet topologies, cables and routers, or web graphs, websites, and hyperlinks. But even for the web, talking about a real network is something not really true, because the website technically doesn't have any existence. I mean, we recognize a website because we are human, and we use a specific URL, and after that you get to a web page. But navigating through different web pages which have the same visual design and share part of the same URL, we recognize it as a website, but it's just a point of view. Technically, it doesn't really have any sense. And it is the same thing for the links. Okay, we may use hyperlinks, but we may use maybe something different. For instance, to rank, to create a graph of the web, it could be also, imagine, on different web pages, you extract the vocabulary, the terms, and you say that a link exists between two pages if they share enough vocabulary in it. So co-occurrence, what we call co-occurrence network. It is very interesting to identify pages or any document that may share a same topic, or maybe to identify which one does not share. Maybe sometimes it is more interesting. So it is also the same problem for the weight. These numbers that you have on the edge, it will mean anything. I mean, in social networks, in general, we will assume that it is the strength of the connections between two persons. If they share many IDs, many friends, many whatever you want. But it is a strength. It could be it maybe, well, it could be something totally different. It will be it could be negative. For instance, do I trust you or do I don't trust you? Here is one of the first social network used in sociology. It is a study of who is dining with who likes who on a dorm. And when you ask it for people, well, it is not on Facebook where if you have a friend with somebody, this other person is friend with you. You may like somebody else, but the opposite is not always true. And so you have different preferences and kind of ranking. Some people get just more popular. That happens. And so here you have the nodes are the persons, the links are if the person likes the other, and you have other elements that I don't know. You have also a layout. Here, the nodes have a specific positions. We'll better see that in visualization, you have many techniques to use the coordinates to encode information and to better start to read, okay, what does it mean? Why do I have this node at the center? Why do I have this one at the periphery? Why two nodes are close together? There's one and there's one. Oh, they have a link. But why do these ones are closed also? They don't. I want your help now. I want you to make a short experiment where you will pick a pen and write on the pen who you know here in this classroom. Just play it. It will be useful for the rest of the course. Just who you know and the full name. Good data. This is data. Not sure if it is very clean, nor if it is complete, but it's still data. I have yes. I started. I can read, but I don't have the vocabulary. I have a short story from my supervisor. One day he was contacted by a historian researcher, and the guy was really interested in networks. He wanted to try to do network analysis with his data. So my supervisor told him, okay, that's fine, but bring me your data. Okay. When he arrived with many shoes boxes, and full of papers. My supervisor, what is it? Well, it's my data. So really, true story. It's not a matter of where the data, what is the support of the data, or how it is encoded. It's still data, and if we can read it, we can process it. The problem is that most of the time the data is not very good. I mean, there will be some errors in spellings or just missing elements. Sometimes the data is not qualified. For instance, I may have wanted to ask you also if you like the person, if you don't like, how you meet this person, where, to better have information attributes about the connection. And I may also collect some information of you, depending on what I find on the internet or what you give. But I won't. But just to say that we can start to build a network in this way. Just imagine what do we want? I mean, here I have the name, and I know if there is a connection or not. It's binary. But we could have many different variations on the relationship. We could have also many other information: gender, nationality, where you live, where you were born, if you have brothers and sisters, where you at school, what's your favorite sport, or other information about what you buy, shoes, etc. All of this dimension in your data may be interested in to model a network. Here, for social network, it seems obvious that the node would be the person, and the link would be the strength of the relation with this person. Maybe you could do something else. What do you think about it? On your data, you have for each, imagine that you have in your spreadsheet one line per person, and with that you have the different columns of data for each person. So okay, imagine here you have 4%, you know the name, the gender, the city. Imagine that, okay, I would say, imagine that some person share some attribute values. For instance, well, they are either male or female, or something sometimes different. But for the city, some people would live in Ekaterinburg, in Moscow, in other cities. But the fact is that they share, they are from the same city. As a social network, we could imagine that we could build another network. For instance, well, the gender, 2 nodes, male, female, not really interesting. But maybe a network of cities. Nodes will be the cities, and there will be a link between 2 cities if for instance, there will be 2 male people from there will exist 2 male people from this city, or maybe that 2 people, just more, it's more direct. 2 people of different cities know each other. Excuse me. But the connection between the cities could be something totally different. If we go back to the list, maybe we could take a brand as a node, and there will be a link between 2 brands if they share enough customers. There could be a link between nations if there are enough people who traveled abroad to one city or another. I mean, the link will totally depend on your study and what you want to observe. And it starts to be interesting because beyond real networks, infrastructure network, internet, or a transportation network, you can build different other networks based on the data you have. And this is how today we'll try to study social network, how we try to study consumer behaviors, how we try to study populations. I mean, sociology is now become hugely quantitative, and we start to have many information of people, how they are connected, what they do on the web, etc. And all of this information put together about different profiles help to better understand. So tell me, can you give me another kind of network you could imagine in life or something in the world, kind of networks that could exist, or you could see your data as network? Hmm? Mm-hmm. Mm-hmm. Yeah. The food web. Who eats who on nature. It's a very dense network. Which species is more connected to each other? What happens if we remove one species? How the network evolve? Is it still connected? Transportations, of course. If there is a problem in one transportation line or in a station, what happens? Epidemics. If somebody gets flu and meet people, travel a bit, what happens? How is the spreading? How does it evolve? How the AIDS started? How it was able to spread? There is a network structure behind it. A network of humans. But also, well, in computers, for the Unix system, the dependencies of Linux packets, or in buildings, which element is depends on which other one. You could imagine many networks depending on your data, but not all networks are interesting to study. It really depends on your use case. So I asked for the organizers to give you a link about the materials of this course, so you'll have the presentation and also raw data. During the second part of the presentation, you will put your hands in Gephi to start to manipulate networks, and I will provide you some data. And one of the data I will provide is a Russian diaspora on the web. How Russian expatriates use the web to get organized, stay connected with the country. It's interesting. So you'll have the website hyperlinks. Okay. So we have seen that we can have positive or negative values on network, depending on the feeling. I will skip this. I think you know already adjacency matrix. So you have many ways to encode networks, but most of the time, we'll use general edge list or something more able to For processing, well, okay, we can see that we can model data as networks. But what kind of question can we answer now? Something different that we couldn't answer with other traditional statistical analysis. Well, it will depend on the properties we can identify on the network. For instance, who is the most central in the network? Of course, it's related to ranking, but not necessarily. I mean, centrality is something very specific. For instance, here, these nodes are central according to maybe the number of direct collections, but it could be another metrics. For instance, the number of shortest paths that go across these nodes, which is called betweenness centrality. Interesting to study, for instance, how an information can spread and what happened if we add another element in the network, or what happened if we remove an important node. We'll talk about, do you know this kind of vocabulary? Degree at degree? Okay. So it's also different ways to study centrality. We'll skip this. Also, well, connected components. Well, it seems obvious, but when you start to get data, and for instance, you are crawling the web, you have crawlers that start from the same seed of websites, and you explore it. You would like probably to have everything connected, or maybe you expect that everything is connected, and sometimes it's not the case for many reasons, technical reasons, something that happened. It's really important to just check this simple fact to understand maybe, okay, something happened very badly during my process, or my data is not so clean. It happens so many times when you deal with data. It's very important to just check the simple facts and see what's going on. Because maybe because some elements are disconnected, there is a real big problem or big finding under it. So, well, I guess you know what is a connected component? Strongly, weakly connected component? All right. Giant component as well. We've seen it, already done. And also something which is very important in networks, okay, how far apart are things? Well, counting it will be, you have different ways to count distances. It will be what we call the geodesic distance, which is just the number of hops between different, to go from one node to another. But it could be also spatial distance, geographic. It will be, imagine if you have locations, or imagine if you apply an algorithm that will position the nodes according to the relationships. That could make sense. So you know the shortest path also? Okay. Density of the network. Well, I will go faster than expected, so we'll play with Gephi after. Okay, and you have finally, before switching to Gephi, different ways to model networks. I mean, all nodes could mean the same thing. I mean, social networks, you have only a node is a person, and that's all. But in cases when you have different type of elements, what we called bipartite networks, or two-mode networks sometimes, you will have maybe customers and products. Well, I have no ideas. This kind of data is much harder to understand. We start to have a very good algorithm on it, but for the visualization, you'll see that you can't already exactly do the same thing. I will stop on this characterization. I want to show you some other example of networks. Maybe you know about the Eurovision. Whose country is voting for who? You see that Russia, so here, how to read this network? First question. Beyond currently I will give you only a few hints. Here, the nodes are positioned in space according to their relationships. So when two nodes have a link in common, they tend to be closer. If they are not linked, they tend to be further. And the links are directed. It means that you will read clockwise a link from Estonia to Russia or from Russia to Armenia. And so you see that Russia receives many votes from Estonia, Ukraine, Turkey, a bit Finland, etc.
What do you mean
Votes.
votes?
So so it is a song contest when the public will vote for a particular singer, and they have the data of, okay, this guy voted and he's in this country. So you see if people from a particular country tend to better like the songs of this country and not the other.
Yeah, because I thought it was like related to politicians.
Oh, no, no. No, no. But you could have also, for instance, coder's graph. So I will switch a bit, but here, 2 years ago, we collected some data from GitHub. Who knows about GitHub? Good. All right. So here we collected the data of who is contributing to which project, and we only kept the most connected part. I will switch to this area. And so, for instance, we started to study, okay, who is connected to who in terms of who is contributing to which project, or who is following who. And we made something better last year. And we tried to identify a geography of languages. So if I zoom out enough, you will see here that, of course, people coding in PHP tend to get more linked with other people who are coding in PHP. But what is more interesting is the borders. For instance, PHP developers are more related to JavaScript, and sometimes, well, other, I still not know, they have Lisp developers, okay, and people working with Python are more linked to people working in JavaScript and C. Well, for C we can easily understand, but you can start to see some kind of effects that you can also, of course, confirm, validate with proper statistics. But it starts to give a sense of what's going on, and this is what visualization is about, how to discover new things, how to verify things that we already know, or maybe how can we verify things that we have an intuition about. Well, another network from the web, this one. We collected the websites which are providing scientific data. They are links to scientific databases, and we collected the hyperlinks between these different websites, essentially in the US, and we created a map of these connections to better see how scientific databases are organized on the web and how they are linked. Can we find clusters? Because, you know, many institutions, laboratories tend to put data on the web. Sometimes they'll also provide hyperlinks to other institutions, other ways to find related data, sometimes not. And having a better sense to understand how this information is organized to better help people to find information and switch from one institution to another may be a tool for decision makers or people who are evaluating what kind of strategy should the institutions have on the web, how to occupy this kind of territory, how to better serve information to people. That may be interesting. So, for instance, that may be useful to identify, well, better, most connected websites. NSF, for instance, receive many connections. But you can also try to identify some kind of clusters, topical clusters. Agriculture, here botany, biodiversity, all about biology in this area. Maybe if I switch here, we tend to see chemistry, health. And if I go a bit on the bottom, something more about Earth, physics. So it's interesting by itself to see how it is structured. And for people who are responsible to create hyperlinks on the web, to better see how it's going on and how they could be better connected. Or maybe for somebody, okay, I'm here, how can I become here at the center? That may be used to evaluate the strategy, how to get a position, how to be well placed on the web. And there is also a very important topic about evaluating scientific publications. For instance, imagine that you can build a network of which researcher is collaborating with who, or what is his research topics? Does it evolve? What are the collaborations? For evaluation, for instance, it can be very interesting to see what is the position of different laboratories. Or it may be a good way to identify novel way to evaluate researchers. For the moment, maybe you know that we have a kind of ranking to identify the really top researchers based on the number of papers who have at least the same number of citations. And so by studying the citations of papers, we can identify which are the topics and how researchers organize this kind of topic. And we did it using a scientific database called the Web of Science to study how researchers are interested in the Arctic. It is a very, very hot topic for in industry of transport and oil, gas, of course. And researchers may have a different point of view about it. So we wanted to see on what are the topics here, where do they publish. And so this is also another map that was useful to identify how this field is organized. For instance, we can have a kind of summary to identify, well, you have the main visualization, the main graph here, with the links that are ranked based on their number of relationships. The bigger they are, the more relationships they get. And what is interesting is that you have also different scientific areas which appear in different locations of the graph. So you can have a way to split the graph according to the different topics and to see if there is real distinctions or if it is just a mix. What is a place of mathematics or physics in this information space? That are kind of questions that can be interesting. Okay. Can somebody help me to start to draw the network by hand on it? Just to start. And there is not so much space here, so it will just last 5 minutes. I need a volunteer. We'll switch more now to visualizing networks and what are the challenges and difficulties in visualizing this kind of data. So just a better way to figure out what's going on and what we want to do before creating algorithms. It's good to start by hand. Seriously? Oh, thank you. I started to feel alone. Okay.
What should I do?
We'll try to pick some people
from small or from big one list?
from small, but we won't do well. For instance, we can start. I don't have a sense of the existing network, so
It's only
let's start.
surnames, I think.
Yeah. We'll start by small ones, but I'm not sure if that will be connected. Well, let's start by only these two.
Okay. Here's no author.
Okay. Yes. No author here, missing data. Well, it's a game.
So I should write names.
Yes, or only the two first letters to have no too much space. And when you have it, you draw a cycle. Yeah. So,
It's not a good example. I have
Yeah.
only surnames here.
okay.
Maybe should
Yes, we'll pick another one. Okay, so let's start by the beginning of it. Yeah. Good data here.
all the list or only the beginning.
Only the beginning, and we'll switch to other. Okay, try this one, or maybe,
Oh,
yeah,
I didn't write who
yeah,
who is it.
yeah.
So if she knows them,
Yes. So
she knows him.
yeah. So draw a circle around each of them, so it will be much clearer. It
Okay.
around and yes,
where
and
should
and
arrow
yes,
here or
and
here?
hmm?
Where should I draw an arrow?
Well,
Here or here?
It will be here. Yes. Okay, let's continue. It was this one.
Okay.
Okay. Let's try the beginning of this one, and
Okay.
I think it will be good.
When there is connection
Mhm.
from him to him and from him to him, should I write an arrow here or make a second one?
It's up to you. So here we are only at the beginning of the network. We processed 2 papers. I still have all of this, and it starts to be complicated. Yes, I think that would be enough.
Okay.
Or maybe,
Once more?
yeah, once more. Yeah.
Maybe from the end of the list, because I think
Mm.
these people were sitting here and they know
Yeah.
each other.
Yeah. Uh, okay. Pick this one. Okay.
Still not what you were expecting.
I did not know. I mean, I don't know the data. It's the first time I try this kind of thing. But well, was it easy to do?
There were only 6
Y-
lists, so
yeah.
it was okay. I think
Mm.
further it will come harder.
Yeah. So we start to have to see many problems here. So you have this network of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are less than 20 nodes, and I think well, it would take much more time to count the edges. What is interesting here is that, well, we had many issues in visualizing, trying to draw this network. For instance, the first one is that we don't know the structure of this network. So how do we position the different elements? We do it in a naive way, totally, by starting by creating links around a specific node and then expanding as long as we continued. But the problem is that we have intertwined connections, and we start to have many links that go from one point of the network to another, and it will be really quickly most impossible to see anything. There are less than 20 nodes. Imagine for a network of 10,000 nodes, for instance. How can we do? We need some rules here. We need some rules on how to position the elements between each other. We need rules on distances. What will mean to be connected if I see two elements which are very far? How can I read easily the connections to better understand who is close to who, or who is maybe forming a group with some other people? Here, it is particularly complicated because almost, well, you have roughly you have an average between 7 and 10 connections per person. On the web, we say that it is roughly about 7 hyperlinks that will go from a website. And so it is totally explosive. You could compute the theoretical number of edges based on this information, but it starts to be very huge. So we have some troubles to identify, to read this network, and we need some more rules. What in general we are interested in is to identify who is close to who belongs to which group, why is a person more central than the other? Is it reflecting a particular ranking algorithm, for instance, or it is a bias because of some statistical properties that we are not aware of? So, well, we have 20 minutes. So we'd like to position the elements so that it makes sense. We'd like to position the elements so that, for instance, we'll start to see different groups, and if some elements are strongly connected, they will tend to be closer. Otherwise, they will tend to be further. So for doing this, we use algorithms that we call layout algorithms. Most of them are of class that is called force-directed algorithm, because it is based on computing a force on each element of the network, and this force will be a vector that will move the element on space. The game here is to identify a kind of equilibrium in this network so that it won't move. Basically, you will compute two different forces on each of the nodes, and you will iterate until there is an equilibrium. You will compute a repulsive force between every element, and you will compute an attractive force on connected elements only. And this is mostly what we'll use in Gephi. So I've badly planned this presentation, and I'm a bit ahead of it. I wanted to enter Gephi properly during the next course. What can I do? Well, okay. I will show you Gephi briefly, and then we'll make the coffee break. And after that, we'll follow much deeper a Gephi tutorial. Well, of course, if you have any questions, don't hesitate. I know this presentation is experimental, and I wanted to better give you some sense about how we could think about networks around when we have to deal with data. So I think it would be also better by just manipulating some data. So when you load Gephi for the first time, you will see this welcome window where you can just start a new project, and you will see the other projects you have recently opened. By default, it provides also some samples about some small networks. Here, I will load a very small network which is based on the novel called Les Misérables from Victor Hugo, where two characters are connected if they are present in the same chapter. But imagine what you could do with words that are present in the same paragraph or in the same also chapters, section of a book, etc. So here this network is very small, 77 nodes and about 250 relations. So I load it, and by default, what I see in Gephi is a mess. I mean, all the elements are placed randomly on the space. Gephi, well, here you have the visualization as a center. And in Gephi, everything around is made to modify the visualization. It's really the core of the software. The primary goal is to create a visualization that makes sense at the end, or because you are manipulating and exploring this network in real time, you will have some new ideas, new questions that will pop in mind, and you will try to quickly have an overview about about what happens. So this network is very close to what we started to draw, with no plan, no algorithm, just like it. So you can zoom in and zoom out with the mouse. I hope that you didn't forget to bring a mouse. Well, otherwise, well, it's possible. I will show you another way. And if you right-click, you can move. So here we'll see that it's mostly in 2 dimensions. It's possible also to activate a 3-dimensional mode, but it's more difficult to see anything in the network. Yes?
Is it possible to zoom in, zoom out without the mouse because they
Yeah. Yes. So
but doesn't work.
okay. So well, in Gephi in general, what we try to do is that common actions are directly accessible, and for non-common actions, it's still possible, but you have to make 1 or 2 clicks more. So here it is. We assume that most people have a mouse, so to still have a slider, we'll expand this panel when you have a visualization option, and here you see that, well, you still have a way to zoom, but it's not perfect.
Where is this panel?
So here at the bottom, you see at the bottom right, there is this icon. Okay, so I want to see much better what's going on with the structure of this network. So I will choose a layout. I said that many layouts exist. Many of them are of class of force directed, but you will find many other algorithms. For the beginning, I will use only a layout algorithm, which is very common, which is called the Fröchterman-Reingold. You will find it in other tools like Guess or maybe Payak if I remember, and I run it. You will see. Okay. So now you can stop it. So I start to see a bit better what's going on here. So I can see that I start to see this node, and this node, who are apparently central, I start to see one group here, one group there, one bigger group here. Well, we can do better. We'll use another layout just to see. It's also a force-directed algorithm, but with different, well, with some differences. So here, I run it, and I still don't see many things. But this layout uses two parameters, a repulsion strength and an attraction strength. If I increase the repulsion, for instance, it is at 200, I put at 2000, nodes will be much further. So it's interesting to see that it's the same network, but another layout provides a different visualization. And here I see clearly, okay, I have this group, I have this group. I confirm that I have these nodes as a center. And just by doing so, I have the feeling about, okay, what is the structure of this network? And that can help me for the analysis. So second, well, I want to know who is involved. And I can have the label of the data. I mean, each node is a person, right? So I will activate the label here. And I will also reduce the size of the labels. So I see that Valjean has many connections. There's also Gavroche. Cosette here. And now I want to know a bit more about this centrality. I mean, okay, apparently the layout placed this node as a center. But is it right according, for instance, to the number of connections? So here I will use a ranking panel and try to, well, just color the elements according to the degree. And I apply here. Full screen. So here I see that, okay, Valjean seems easily the first of the nodes, the one who was most connections, followed by, Gavroche, etc. And at the periphery, you have the elements who have only one connection. We can also change the size of the elements to make the thing more easy to read. So here, select the degree, I can select different sizes. Change, because it's a bit too large. And so now I have the structure and I have a direct visualization on which node is the most central, the most important according to the degree. This one. That's obvious now, but it was not the case at the beginning. But well, we still have to zoom to see the labels. We can do a little improvement here by changing how labels are rendered. So here I will select to have the labels according to the node size. And so now I can read my labels directly also. Okay. That start to be good, but we still have a problem. Do you see here? Nodes are, it's not easily readable. So to improve the readability, we'll activate an option of the Force Atlas to take the size of the nodes into account in the layout so that it doesn't overlap. And this is the option adjust by size. I can run it. Now it's much better. But it is shaking. What's happening? Well, I told you that the algorithm will try to find an equilibrium state. He's not able to find it here. Or maybe it's not very... he was able to find it globally, but locally he got some trouble. So we can change it by, for instance, reducing the speed of the layout. So for instance, going from this one. So which is just about reducing the forces by instead of having the forces computing with a factor of 1, we have a 0.1, and here it seems to be better. Okay, we can stop it. So what you've learned here is one algorithm that is able to show you the topology of the network very easily, and you will start to be able to notify visually some groups and the most important nodes. After the coffee break, we'll go much deeper about computing statistics, page rank for instance, filtering the network to only see some specific part of the network according to the query we can make, and how we can create good images to export for the web or for publication. And we'll also go deeper about the visualization part, what is exploring network, what we want to achieve, what kind of question we are able to answer, what are the problems also with this visualization. Because we can, I mean, we are human and we only see what we really want to see. So there are many things that in the visualization, some things get obvious, but some others we just don't see them. And sometimes we interpret the visualization in the sense that we prefer. And, well, we'll see it much after the coffee break. Thank you.